In the pursuit of more efficient power generation, even small changes in thermodynamic processes can lead to significant improvements. Over the decades, engineers and scientists have refined classic cycles, adding stages, redirecting flows. This is one of them. In the quest for higher thermal efficiency and better turbine reliability, engineers developed the reheat cycle, a practical enhancement to the ideal Rankine cycle. It addresses the major drawback of steam expansion in turbines: increased moisture at low pressure stages. By reheating the steam between expansions, the cycle maintains better thermal performance and extends the lifespan of turbine blades. It's a solution where thermodynamics meets engineering design.
The next engineering innovation that I want to uncover is the crucial invention that turns steam into movement. It's an invention that was so efficient and so effective that 100 years later, it's still being used in modern power plants. It's a steam turbine.
The generation of electricity through steam turbines forms the backbone of many countries' energy infrastructure. The Rankine cycle, although effective, has its limitations. As steam expands and does work, it cools down and partially condenses, producing moisture. This moisture can severely damage turbine blades and reduce overall efficiency. To counter this, the reheat cycle was introduced. This innovation not only reduces turbine wear and tear, but also increases the average temperature of heat addition, boosting efficiency. Today, reheat cycles are standard in thermal power stations, especially in plants above 100 megawatts. Before we go further, let's briefly revisit the basic Rankine cycle. It consists of four key processes: pressurizing liquid water in a pump, heating it into steam in a boiler, expanding it in a turbine to generate work, and then condensing it back into liquid in a condenser. In the ideal cycle, heat is added at a constant pressure, and steam expands isentropically. However, in reality, this expansion causes steam to reach low-quality states, especially near the condenser. The result? Wet steam, damaging and inefficient. So what exactly is the reheat cycle? In this modified cycle, the steam doesn't expand through the turbine in a single step. Instead, after partial expansion in a high-pressure turbine, the steam is sent back to the boiler or a separate reheater. There, it's reheated to a high temperature, often close to the initial superheat temperature, but at the same pressure. The now dry, superheated steam enters the low-pressure turbine, where it undergoes a second expansion. This two-stage expansion not only improves performance, but also significantly reduces moisture at the final exhaust. If you look at the TS, known as temperature entropy diagram, you'll notice two distinct expansion paths, clearly showing where reheating occurs. On the TS diagram, the reheat cycle forms a more spread out loop, indicating higher average temperature during heat addition. This higher average temperature is key to improving thermal efficiency, as suggested by Carnot's theorem. In the HS or Mollier diagram, the expansion paths before and after reheat show how the enthalpy drop is split across two turbines, leading to increased work output and better control over steam quality. The reheat cycle offers multiple advantages. First, higher thermal efficiency. This is because heat is added at a higher average temperature. Second, reduced moisture content, ensuring steam remains dry enough in the low pressure turbine. Third, extended turbine blade life. Less moisture means less erosion. Fourth, increased work output. Two expansions give more shaft work from the same steam. And lastly, improved operational flexibility. Plants can adjust reheat temperatures to optimize performance during partial load conditions. All of these factors make the reheat cycle not just a luxury, but a necessity in modern power plants.
Good day to all. My name is Colin Brandon O. Asio, and I'm about to present an example and a little bit of background recap on the ideal reheat cycle. So let's begin. So let's proceed to the schematic diagram where I'm about to show you the schematic diagram of the ideal reheat Rankine cycle with one stage of reheating. So as you can see, this is a modified Rankine cycle that improves efficiency and reduces moisture content at the turbine exhaust. Let's dive into the schematic and see how this cycle works. So in this cycle, we have standard components of a Rankine cycle, plus one additional turbine and a reheater. The main components are first, labeled as QAB, known as the boiler, where heat is added to generate high pressure steam. Second is the pressure turbine, WT, where the steam expands partially and the steam expands further. Next is QAR, or known as the reheater, where the partially expanded steam is reheated. Next is the condenser, where the steam is condensed into saturated liquid. And lastly, the pump, WP, which feeds the water back to the boiler. Now let's walk through the process step by step. For the TS diagram, let's look at the flow through the system using state points. We'll label them for 1 to 6. So as you can see here, we have drawn a TS diagram. Here's our 1, our 2, our 3, our 4, our 5, and our 6. So from state 1 to 2, let me draw here 1 and 2. It is a high pressure liquid water is pumped from the condenser to the boiler. This is an isentropic compression. Next is state 2 to 3. So 2 to 3. So in the boiler, heat is added at a constant pressure and water turns into high pressure, high temperature steam. Then 3 to 4, the steam enters the high pressure turbine and expands isentropically, producing work. And state 4 to 5, after partial expansion, the steam goes into a reheater where it is reheated at constant pressure to the original turbine inlet temperature. And lastly, 5 to 6, the reheated steam then enters the low pressure turbine where it expands again isentropically down to the condensed pressure. And lastly, 6 to 1, Finally, the steam is condensed in the condenser into saturated liquid, completing the cycle. This two-stage expansion with reheating increases the average temperature of heat addition and reduces moisture content at the turbine exit. Now let's break down the thermodynamic processes of the ideal reheat cycle step by step. So as you can see here, for processes 1 to 2, partial isentropic expansion in the turbine S equals C. So here, from point 1 to point 6, or process point 1 to point 2, partial isentropic, entropy S is constant. That means it's an isentropic process. High pressure steam from the boiler enters the high pressure turbine and expands, producing work. The steam loses pressure and temperature, but ideally there's no entropy generation, meaning no losses due to friction or heat transfer. This is where we get our first chunk of useful work. Next is process 2 to 3. Reheating at constant pressure P is equal C. So here, pressure P is constant, known as an isobaric process. The steam is sent back to the reheater where more heat is added without increasing the pressure. So reheating improves efficiency and reduces the moisture content in the next expansion phase. Next is 3 to 4, complete isentropic expansion in the turbine, S equals C. Here, entropy S is constant, another isentropic process. The reheated steam enters the low pressure turbine and expands all the way down to the condenser pressure. So more work is extracted in this stage. This is the second major expansion phase, and again, we assume it's ideal with no losses. Next is 4 to 5, constant pressure heat rejection. P is equal C. So here, the steam exits the turbine and enters the condenser, where it gives off heat and condenses into a saturated liquid. This is where the waste heat is removed, typically into a cooling tower or river. Next is 5 to 6, adiabatic pumping, S equals C. So entropy S is constant, again, and another isentropic compression. The feed water pump raises the pressure of the saturated liquid to a boiler pressure without adding heat. So the pump consumes a small amount of work to send water back to the boiler. And lastly, process 6 to 1. Constant pressure heat addition in the boiler, or P is equal to C. So pressure P is constant, isobaric heat addition. The high pressure water is converted into high pressure, high temperature steam in the boiler. This restarts the cycle with heat input from fuel combustion, typically in a furnace. So here we have the ideal reheat cycle analysis. So total heat added, QAT. This is our schematic, short schematic diagram for our steam boiler, where QAB is approaching towards inner face, then H6 is provided outside the ball. By energy balance, following the calculation, energy in is equal to energy out, QAB plus H6 is equal to H1. Then we derive it, we arrive to the equation QAB is equal to H1 minus H6. So here's another schematic for our reheater. QAR approaches inside, and H2 approaches inside, outside is H3. So by energy balance, here's our equation. Energy in is equal to energy out, where QAR plus H2 is equal to H3. And with this analysis, we need to find QAR, so we arranged our equation so that we can get the value, and then H3 minus H2. So for total heat added, QAT, QAT is equal to QAB plus summation and QAR. So by energy balance, energy in is equal to energy out. H1 plus H3 is equal to WT plus H2 plus H4. So by rearranging the equation, we arrive at this. WT is equal to H1 plus H3 minus H2 minus H4. So here is our short schematic for energy balance. So by energy balance, energy in is equal to energy out. H4 is equal to QR plus H5. Rearranging the equation, we arrive at that answer. QR is equal to H4 minus H1. So for our pump work, we have our short schematic, WP, H5, and H6 outside. So using heat exact pump work by energy balance, energy in is equal to energy out. So WP plus H5 is equal to H6. Rearranging the equation, we arrive at this. For our steam rate, we need to follow with the formula MC is equal to mass of steam over power, or simply known as MS over P. And MC is equal to MS over MS times W net, so work net. So unit analysis, MC is equal to kg over S times 3,600 seconds over 1 hour. This is simply conversion for 1 hour from hour to seconds. And kilogram over seconds times kilojoules over kilograms. So by rearranging the equation, deriving them, MC, we arrive at the answer MC is equal to 3,600 over W network, or simply kilogram over kilowatt hour. And W net must be in kilojoules over kg. So that's like our typical standard unit for solving W net. So ideal reheat engine analysis, A steam rate, ME is equal to 3,600 over WT, or simply kg over kilowatt hour. So next is using approximate pump work. So WP is equal to VF5 times P6 rather, minus P5. And that cycle work, W net is equal to WT minus WP. And overall cycle thermal efficiency, EC is equal to W net over Q80 times 100. So by energy chargeable against the engine, so we need to use the summation now because we need to extract the values and get its summation, just like computing for our electricity bill. So thermal engine efficiency is equal to E is equal to WT over EC times 100. Now let's proceed to a sample problem for our ideal reheat. So here is our sample problem. In an ideal reheat cycle with two stages of reheating, steam turbine receives 10 kg per second of steam generated at 12.0 megapascal in the instant 580 degrees Celsius. The reheater pressures are 5.0 megapascals and 3.0 megapascals. Steam leaves each reheater at 480 degrees Celsius. Condensation occurs at 0.02 megapascals. So we need to determine A, B, C, D, E, F, G required. First is schematic MTS diagram. B, enthalpies, kilojoules per kg and each temperature. C is total heat added. D is turbine and pump work in kilowatts. E is network and energy chargeable kilowatts. And F is overall cycle thermal and engine efficiency in percentage. And lastly, cycle and engine steam rate, kilogram per kilowatt hour. So to begin with, we'll start with our schematic diagram. So here it is. So as what we can see in our schematic diagram, there is a boiler, a pump, condenser, and two reheaters now, and a turbine. So this is different compared to the previous example. So let us understand, or let's begin by understanding the schematic diagram of the ideal reheat cycle. So this cycle is an improvement of the basic Rankine cycle. It is designed to increase efficiency and avoid excessive moisture in the turbine exhaust. So as what we can see here in process 1 approaches to 2. So here it is the high pressure steam from the boiler enters the first stage turbine and expands doing work. So this is the first expansion stage. Next is process 2 to 3, where the partially expanded steam then enters the reheater, where it is heated again at constant pressure. Next is 3 to 4. So this is the reheated steam enters the second stage turbine, where it undergoes further expansion, generating more work. And then process 4, 5, and 6, steam exits the turbine and goes to the condenser, where it is cooled and condensed at constant pressure. Process 6 and 7, the condensate is then pumped to an intermediate pressure by the feed pump. Process 7 and 8, it is then further pressurized to the boiler pressure by the second feed pump and re-enters the boiler to complete the cycle. We also see heat interactions. So let me erase this first. So here, QAR1 and QR2. This one and this one. So heat added in the boiler and reheater. For QR, heat rejected in the condenser. WT, total work done by turbines. And WP, work input to pumps. Proceed to the TS diagram. So we're going to analyze the TS diagram, which corresponds to the same cycle. So here it is. So for the TS diagram, we can see our 1 and number 2 here. So this line 1 to 2 is an isentropic expansion in the high pressure turbine. For 2 to 3, it is a constant pressure heat addition in the reheater. For 3 to 4, it is the isentropic expansion in the low pressure turbine. And lines 4, 5, and 6, it is the condensation at constant pressure in the condenser. And line 6 to 7, it is the isentropic compression in the first pump. Line 7 to 8, it is the isentropic compression in the second pump. And 8 to 1, constant pressure heat addition in the boiler. Notice the temperature here. What is the temperature? As what you can see, steam is reheated to a high temperature again at point 3, which helps maintain the average temperature of heat addition, thereby improving the thermal efficiency of the cycle. The reheat process allows the cycle to produce more turbine work without decreasing the cycle's efficiency due to excessive moisture at the turbine exit. So, erase this. So let's proceed to our calculations. So at point 1, here at point 1, its condition is superheated steam. P1 is equal to 12.0 megapascals. T1 is equal to 580 degrees Celsius. So since its superheated steam and pressure and temperature are known, you can directly look up the enthalpy and entropy from superheated steam tables. First is to go to the superheated steam tables for water, find the tables for 12.0 megapascals, known as 120 bar, and look under the temperature row for 580 degrees Celsius. We read off the values for our enthalpy should be close to 3557.5 kilojoules per kg, and our entropy should be close to 6.7448 kilojoules per kg Kelvin. These are your values for point 1. For point 2, 5 megapascal, S2 is equal to S1 is equal to 6.7448 kilojoules over kilojoule K. So our condition is superheated steam. But in this equation, we need to use interpolation. So here is our given value, our table value from our steam table. So we need to arrive at this answer. We need to remember this for our H2, and for our temperature T2 must be 428 degrees Celsius. Now we need to solve this. So for our calculation, for interpolating H2, H2 is equal to H low plus S2 to minus S low divided by S high minus S low. Then we multiply it by H high minus H low. We then plug in our numbers. H2 has the value of 3, 2, 4, 4.4 plus, erase this, x plus 6.7448 minus 6.7172, and we divide it by 6.7517 minus 6.7172. Then after arriving at the answer, we multiply it by 3268.5, 68.5 minus 3244.4. So by inputting it to our calcu directly, we will arrive at the answer for our H2 with the value of, for our calculation, H2 is equal to 3263.68, which is correct based from our given answer earlier, per kg. Next is solving for T2, where we need to solve for T2 using the degrees Celsius, which is by solving for 20 plus same as 6.7448 minus 6.7172 divided by 6.7517 minus 6.7172. Then we multiply it by 430 minus 420. So by inputting that to our calcu, we will arrive at exactly 428 degrees Celsius. So we are correct. So is equal to 428 degrees Celsius. So we proceed to at point 3, where this is the value of it. 5 megapascal at T3 is equal to 480 degrees Celsius. Our condition is superheated steam. Again, as we go back to our steam table, we will arrive at getting H3 for 3,387 kilojoules per kg, and S3 is 6.9145 kilojoules over kgk. So at point 4, P4 is equal to 3 megapascal, S4 is equal to S3 is equal to 6.9145. So here we need to show calculation again for our interpolation to get the value for H4 and for T4, known as the temperature of the steam entering the second reheater. So for step 1, the solution is S is equal to H4 is equal to H1 plus S4 minus S1 divided by S2 minus S1. Then multiply it another by H2 minus H1. So with that formula, we will be able to get the values to solve for H4. So here we solve by starting as for the H1 value, which is 3,20880.0 rather, plus 6.9145 minus 6.8870 divided by 6.9212. Then multiply it by, oh, this is wrong, we need to minus it first. Sorry. We need to minus it first. So 9212 minus 6.8870. Then we multiply it by 3230.9 minus 320.8.0. Then by solving it, we'll arrive at an answer for our H4 as H4 is equal to 3,226.41 kilojoules per kg. And for T4, you'll get the value for 390. So T4 is equal to 390 plus S4 minus 6.8870 divided by 6.9212 minus 6.8870. Then multiply it by 400 minus 390. So T4 will be 398.04 degrees Celsius. 398.04 degrees Celsius. And by looking back to our answer earlier, we arrive at the same calculation and we arrive at the same answer. So let's proceed. At point 5, the steam has a pressure of 3.0 MPa and the temperature of 480 degrees Celsius, indicating it is in the superheated region. Since both pressure and temperature are known, we can look up to the corresponding enthalpy and entropy values from the superheated steam tables. From the tables, the enthalpy H5 is found to be 3411.5 kilojoules per kg. S5 is equal to 7.1749 kilojoules per kgK. These values are used to define the state of a steam entering the next turbine stages or process. This step is essential for calculating the energy changes and efficiency in the cycle. At point 6, P6 is equal to 0.02 MPa, S6 is equal to S5, 7.71749 kilojoules per kgK. Our condition here is wet mixture. So by following this equation and formula, plugging in the values, we arrive at x equal to 0.8963. To determine the steam quality, we use the entropy formula. So this value represents the energy content to wet steam exciting the low pressure turbine. It's a critical step for evaluating turbine work and cycle efficiency. So here, for solving for H6, so we arrive at the value H6 is equal to 2365.1443 kilojoules per kg. So next it is at point 7, P7 equals to 0.02 MPa. Our condition here is saturated liquid. So this represents the fluid's energy after compression, preparing it to enter the boiler for the next cycle. So plugging in the values, we get the value of H8 here at point 8, condition compressed liquid. So plugging in the values, we get WP is equal to 12.1861 kilojoules per kg. And for H8, so H8, we get this value 263.5861 kilojoules per kg. So we proceed at the total heat added, or letter C, in our calculation and rejected kilowatt. So what is this problem? So what is it trying to teach us? Well, solving for total heat without knowing the heat added and rejected, you can't evaluate how efficiently the system converts heat into useful work. So according to the first law of thermodynamics, the network output is the output equals to the network is equal to heat added minus heat rejected. So this balance is the foundation for verifying that your cycle design or simulation is correct. So heat rejected often goes to the environment, example cooling water. Knowing this help assess thermal pollution, cooling system load, and operating cost and fuel requirements. So in summary, calculating total heat added and rejected in kilowatt allows us performance, evaluation, and proper design in the thermal power systems. So let's proceed for heat added in the boiler. So QAB by following the names principle and solving for our output in the boiler H1 minus 2H8. So we arrive at 3293.9139 kilojoules per kg. Then the summation, like I said earlier, for calculating kilowatts, we need summation just like our electricity bill. So 1 to 2, summation of QAR is equal to QAR plus QAR2. Then solving for the equation, we then get the value of 308.4063 kilojoules per kg. Then QAR H3 minus H2 plus H5 minus H4. Then solving this to our calculator, plugging in the values, we get QAR as 308.4063 kilojoules per kg, similar as this one. Just try to recheck it. So solving for QAT and QW, We then solve for this QAT for the summation of QAR. So solving it by applying the thermal energy principle, and for solving for our energy balance for QR, we then multiply and canceling kg over s and multiply it by 236.51143 minus 25.1082. So by this we get the answer of 21137.443 kilojoules per second. And for the turbine and pump work, kilowatt, so here it is. WT is like the total summation, or like the summation for H1, H3, and H5, but the minus for H2 minus H4 and H6. So this we arrive at 3T3557.5 plus 3387. Plugging the values, we get our WT, work turbine. And for work pump, applying its principal equation, we then plug in WP for 1 to 1. Plugging in the values, we get 1 to 1.861 kilojoules per second, or kilowatts. And for our network and energy chargeable kilowatt, so solving it, W net is equal to WT minus WP, plugging in the values, and then we arrive at 14885.759 kilowatt. So for solving for energy chargeable in kilowatt, since EC enthalpy of steam from boiler summation of QR, EC is equal to following the same principle for solving the energy balance for QAR. This plugging in the values, cancel kilogram, then we plug in the values, and EC is equal to 36145.063 kilojoules per second. So calculating turbine and pump work in kilowatt is essential for analyzing the energy performance of a Rankine or reheat Rankine cycle. This net power is critical for calculating the thermal efficiency of the system using the ratio of net work to heat added. Knowing turbine and pump work also helps engineers design size equipment like turbines, pumps, and generators. So this enthalpy of steam refers to the total heat content of the steam per unit mass, which includes both the thermal energy and the energy associated pressure, typically shown expressed in units of kilojoules over kg. So following the first law of thermodynamics, the basic part or the chunk of this problem to systems like steam turbines or boilers, it helps determining how much heat is added or extracted to the boiler. To follow is the overall cycle thermal and engine efficiency. So solving this equation, plugging in the values. So this is we need to remember this. This is the equation for EC, W net over QAT times 100%. So we get 41.3227% or 41.3. Since solving for E, so WT over EC times 100, E is equal to 41.52. So much close related values here. And lastly, for G cycle and engine steam rate, solving for MC is equal to 3600, or like the conversion for 1 hour to seconds, over W net. As stated in the discussion, W net must be in kilojoules over kg, and MC is equal to 36 over 1488.5759. So this is our value earlier for our W net. And then solving it and computing it, transforming it into another unit, there must be a conversion, and we arrive at 2.4184. Solving for ME is 36 over WT, and plugging in the value of WT, then dividing it, will arrive at 2.3988 kilogram over kilowatt hour. So this sums up our presentation on an example of a reheat ideal Rankine cycle. And thank you for watching, and please subscribe to our video. Thank you.
Example 1. First, we define the given and required values. We have 3 megapascals, 500 kilopascals, and 9.59 kilopascals for the high pressure, reheat pressure, and condenser pressure. Temperature limits are also given, with the temperature of steam at the input of the turbine is at 600 C and 45 C for the condenser. The required values are the exit temperature of the reheat stage, the output power of the turbine, and the rate of heat transfer in the boiler. Next, we draw the illustration to aid us in visualizing the processes and the cycle as a whole. Solving for the reheat exit temperature. First, to determine the temperature at state 5, we need a property that describes the state. It can be enthalpy, internal energy, entropy, or volume, so that we can define the other properties related to the state. The steam expands in the turbine as an isentropic process, so the entropy at states 5 and 6 are equal. So the entropy value at state 5 gives us a property in which state 6 can be described. Given the pressures at state 5 and 6, we can then use their respective pressures to determine the entropy at state 5. The condenser pressure is not directly given in the properties table, so we interpolate using the equation, where XA, XB, and XC are the top, middle, and bottom values respectively, the same as YA, YB, and YC. Since the turbine exit steam is a saturated vapor, we only need to interpolate SG, which then is 8.1654 kilojoules per kilogram Kelvin. Values other than 9.59 kilopascals are given in the table. We transfer the value of Sg to determine the temperature of the exit steam from the reheater, also using interpolation with values given in the properties table other than Sg. Solving for the turbine power output and the boiler heat transfer. We arrange the enthalpy values in a table so that it is easier to reference once we calculate the turbine power output and heat addition in the boiler. Before the power and rate of heat transfer is determined, we need the mass flow rate, and using the output heat transfer, we can calculate for it to be 4.177 kilograms per second. There are 2 turbine stages, from 3 to 4 and 5 to 6. We substitute the values and get the turbine power output to be 6,490 kilowatts. There are also 2 heat addition processes, from 2 to 3 and 4 to 5. Following the heat addition equation, we get 16,477 kilowatts. For example 2, we first need to list the given and required values and draw the illustration. Similar to example 1, we determine the enthalpy values at each state and interpolate as needed. Then list in a table the enthalpy values of each state. To determine the network output, Note that the turbine has 3 stages from states 3 to 4, 5 to 6, and 7 to 8. The pump works from states 1 to 2. To determine the heat input, take into account the 2 reheat stages. It would then be 3,776 kilojoules per kilogram. The thermal efficiency is simply the ratio of its network output and the heat added to get 35.98%. We assume a turbine efficiency of 80% but has values similar to that of example 1. First, we draw a new illustration of the TS diagram to show the changes with respect to the turbine efficiency that accounts for the new enthalpy values. To find the actual exit enthalpy values of the turbine, we use the turbine efficiency equation in which it is the ratio of the actual and the ideal work output. Then list the new enthalpy values into the previous table where A denotes the actual state. So the additional states are 4A and 6A at the high pressure and low pressure turbine exits respectively. Then determine the required values following the same equations used in example 1, but now using the actual states 4A and 6A. So the total turbine power output should be 4,799 kilowatts and the boiler heat transfer should be 12,701 kilowatts. The mass flow rate is different from the previous example since the exit enthalpy at state 6A, where the steam exits the low pressure turbine, has changed. From example 2, find the thermal efficiency of the cycle assuming the pump has an efficiency of 80%. First, determine the actual exit enthalpy of the pump. In contrast to the turbine efficiency equation, the pump efficiency equation has its ratio as the ideal work to the actual work. Then substitute the new actual enthalpy value at state 2A into the network and heat addition equations. The values remain the same except for enthalpy at state 2, which is replaced by enthalpy at state 2A. There is no significant efficiency decrease as the pump work accounts for a very small percentage in the network output, where the turbine output is large enough that pump work does almost no work.
The Rankine cycle with reheat proves that smart engineering can stretch every drop of steam for maximum power and efficiency. From reducing moisture damage to increasing turbine output, it's a brilliant balance of science and practicality that keeps our power plants running cleaner and stronger. Whether you're a student, an engineer, or just someone curious about how we generate electricity, understanding this cycle is a step toward appreciating the systems that power our world. Thanks for watching.